So this concept map shows a kind of summary of the different reactions of alcohols that we learn about in this chapter. So we have the preparation of alcohols. So how do we make an alcohol? An alcohol can be frequently made by hydrogenating an aldehyde or a ketone. So we've learned hydrogenations before because we learned about hydrogenating an alkene or an alkyne to saturate it. So it's actually really pretty similar. It's like one of those addition reactions where we open up the double bond and then we have the jazz hands, and each atom now can grab onto something new, except since one of those atoms was an oxygen, when it grabs onto a hydrogen, it makes an alcohol. So see a lot of overlap in the organic families now. We can also prepare an alcohol by hydrating an alkene, which we learned about in chapter 11. You open up the double bond, and one side grabs onto a hydroxyl group and the other side grabs onto a hydrogen. We can reverse that. If we start with an alcohol, we can dehydrate it to create an alkene, essentially in a reverse of that reaction where we give off the hydroxyl group, we give off the hydrogen, and we close the drawbridge. We close the two single bonds into a double bond between the two carbons again. So for hydration of an alkene, we have to consider Markovnikov's rule, and for dehydration of an alcohol, we have to consider Zaitsev's rule, which are essentially really similar rules, but for different kinds of reactions. And then we have the oxidation of alcohols using usually an oxidizing agent, which could be a biological enzyme, as we see in the human body, or something like inorganic, like potassium permanganate or sodium dichromate and so forth. If we are starting with a primary alcohol, we will oxidize it to an aldehyde. We're going to learn a lot more about these structures coming up, but in the meantime, they have a carbon double bonded to an oxygen and a hydrogen. If it's a secondary alcohol, we can make a ketone, which is very similar. It's a carbon double bonded to an oxygen, but we end up with a carbon group on either side, not a hydrogen. So some type of carbon group, some type of carbon group, could go on. And then if it's a tertiary, we actually get no reaction. So you can add the oxidizing agent, but nothing actually happens. So no reaction. So I want to explore these just in a tiny bit more depth and look at some examples. So to start with, I want to talk about actually what does this look like? We write the reactions a lot, but we aren't getting to see it necessarily. So I wanted to include just a quick image and a video of the actual process. So here you can see potassium dichromate here. You do not need to memorize that name or anything, though you should recognize it as an oxidizing agent. And it is a kind of an orange or a brown color depending on the concentration of it. And here we have a sample of ethanol, which is a primary alcohol. When we add the chromate into the alcohol, and it does require heat, it's not necessarily an instant thing, if we have a reaction, we're going to be able to tell because the oxidizing of that alcohol, so the alcohol loses electrons to that oxidizing agent, which gains them, and that causes that chromate ion to actually take on a different color in the new ionic compound, the precipitate that it creates. So when we see an orange color and then it goes to kind of, sometimes it's bluish green or maybe a brown, we know that oxidation has occurred. Now, what is produced in here? If we were to test this substance and see what we have, instead of having ethanol, CH3, CH2, and then we'll do my OH there. Instead of having ethanol, I probably have an aldehyde, because a primary alcohol can be oxidized to an aldehyde, but I also might have carboxylic acid, because aldehydes themselves actually can be further oxidized. So you can actually start with an alcohol and then get all the way to the carboxylic acid. And we can see evidence that that happened at the macro level by this color change. If this had been an alcohol that wouldn't react, that wouldn't be oxidized, I'd expect it to have retained that kind of orangish brown color. Now, another common oxidizing, an inorganic oxidizing agent that we use, so is that, you can see it right there, that potassium permanganate. That's the name of it. And I want to show you just kind of what that looks like. Make sure that we don't get any of the music going. It does have some weird background music. We don't need to hear that. So here we have potassium permanganate just being added to like water. So you can see, you know, some type of control group, that it turned it purple because potassium permanganate happens to be a purple, a really cool, really very pretty purple substance. Now notice when we add it to the alcohol, which is also ethanol in this case, that it goes purple for a little bit, but the color does ultimately disappear. As opposed to when we put it in the control group and it stayed purple, so that change in color gave us evidence that that oxidation was going on and that our ethanol was being oxidized. So we have some visual, qualitative evidence that oxidation was going on. So let's do some practice problems for oxidation together. Again, I'd always encourage you in a situation like this to pause the video and try to solve on your own and play when you get stuck or when you want to check your answers. So this says, name the following alcohols and complete the oxidation reaction if possible. So if we're going to write NR, no reaction, if it wouldn't happen. So we would evidence that in the last two examples with the chromate and permanganate by the lack of the appropriate color change if we added it to the alcohol. So naming, find the longest carbon chain with the hydroxyl group. So 1, 2, 3, 4. So this is going to be a butanol. And the substituent and the hydroxyl group are on the same. So it is 2-methyl butanol. 1, 2, 3, 4. 1, 2. Yep. Okay. So you might notice this like brackets or parentheses with the O. That's just a way to say some oxidizing agent. You're welcome to use that because I'm not expecting you, and you wouldn't necessarily know when we're going to use what. And it could be, if we're talking about a biological system, it could be an enzyme. So this doesn't stand for oxygen. It just stands for oxidizing agent. So when we oxidize an alcohol, what I would recommend doing is find your carbonyl carbon. Find your carbonyl carbon right there. And recognize that it is the carbonyl carbon that's going to play a really critical role. So before we try to do any changing, let's classify this alcohol. So when I find the carbonyl carbon, I might notice that it is attached to 1, 2, 3 carbons. So what is that? What does that tell us? Well, it's a tertiary carbon. These are my absolute favorite kind of problems to do because the answer is no reaction. I don't have to do any more thinking. Because if I took this 2-methyl butanol and I put, let's say the potassium permanganate in it and it turned it purple, it's going to stay purple and no reaction is going to happen. So moving on to the next one. So let's start by classifying because that way we don't have to do as much work. So here's my carbonyl group. And my carbonyl group is attached to only one other alkyl group. That's the word I'm looking for. So it's primary. So that I know that it can react, and you might already kind of be like, okay, and it's going to make an aldehyde. So let's look at why and how that happens because that can help us a little bit. So find your carbonyl carbon, and okay, so you've got your hydroxyl group is going to be involved, and we're not going to get into the mechanism of exactly what's happening, but it helps us to like find that group, and then you're going to actually, in this case, and this is a big difference between it and a dehydration reaction, it's actually the hydrogen of the carbonyl carbon that reacts. And that's actually why tertiaries don't have a reaction. There's no hydrogen for them to react with the oxidizing agent in the way for this reaction to occur. So we are going to make water by losing one of these. And don't worry about do we lose this whole thing to make the water or what? Because we do want to keep an oxygen. And I don't want you to worry about did the oxygen come from the oxidizing agent or is it this oxygen? Just know These two leave and we end up, you know, making water from it. And then I'm going to then, like, if you think about what I have here, I'm going to draw that carbon here, and I've got this hydrogen, and it's still single bonded to an oxygen, and it's still bonded to this stuff on the other side. But neither my carbon nor my oxygen have full valence shells anymore. Like, really what they have is each of them has this one electron left because the hydrogen left, and remember they were sharing these two. So we had 1, 2, but the hydrogen took one. So these, think of these electrons as moving down here to create a new double bond. So I'm going to move my structure up here. So instead, I take this, focusing on this side of the molecule, and I end up with that. The oxygen has lost its hydrogen and the carbon has lost one of its hydrogens. Now the rest of the molecule is left unchanged. So I'm just adding what was there. These methyl groups are unaffected. The reaction only occurs there where near my carbonyl carbon. So I'm just adding those. So this is the aldehyde product. Now, depending on what the direction said, since it does say complete oxidation, there actually is one more product. If this one further reacts, we could get instead, or in addition, it's going to look really similar, a carboxylic acid instead, which is the most oxidized species there, in which case this hydrogen's leaves and is replaced by a hydroxyl group. So last one, I can see really quickly that this reaction is possible because there is still a hydrogen here on my carbonyl carbon. You can see here this is a secondary. It would be named, let's see, 1, 2, 3, so 2 propanol. I forgot to name this one up here. Be 1, 2, 3. So it would be 1, 2, 2,2-dimethyl 1. If you know, sometimes we leave off the 1 propanol. All right, sorry. Moving down here. So if my hydrogen and my hydrogen are going to leave reacting with the oxidizing agent, there's an oxygen in most of those to make water, and then that they come down and form a double bond. I end up with CH3 carbon. We end up with a double bond there, CH3, and you'll notice it's a ketone. This is a ketone. We'll talk about naming ketones next week. So we see a tertiary has no reaction. A primary makes an aldehyde, which may further react to a carboxylic acid, and a secondary can react to make a ketone. So that's a little bit more detail on the oxidation of alcohols.